All right. So welcome today. Today's Wednesday. I have to apologize. I have to make I made an error of my own scheduling, and so actually I scheduled a doctor's appointment for tomorrow. I've got to get it done. So what I'm going to do is instead of having a lecture tomorrow at 9, I'm going to have one instead of Thursday. I'm going to have one on Friday at 9. And of course, if you can't make it on Friday, that's perfectly fine. Um, but I just wanted to give you sort of a heads up that the lecture for Thursday will actually appear Friday. Okay. Um, so I apologize for that. I didn't realize that um, I had scheduled it for that. But with the slowdown in a lot of industries, it sometimes takes a month or two to get a doctor's appointment. Okay. So what I want to do today is on Monday, we covered sections 3.1, I'm sorry, 3.2, which was percent composition. And then 3.3, which was the balancing of equations. So what I want to do today is work on the mole and molar mass, and then combustion analysis. Okay, and then that will leave, so this is today, and then that'll leave 3.6 and 3.7, which is, amounts of reactants and products, and then limiting reactants. So that'll be on Friday. Okay. And then that'll get us through the chapter. Okay. So let's talk about the mole and the molar mass. There's a few different types of problems that Alex will work with you on that one. So let me see if I can open up the first one. Okay, so the first one is using what's called Avogadro's number. And, there's a couple of different aspects of this. So let me move that out of the way first, and let's try this. Okay, so let's talk about Avogadro's number. So that's this section right here. So Avogadro's number is just, it's a constant. It's a physical constant in nature. You can think of it as like, the speed of light is a physical constant. The, well, there's a bunch of ones in physics that you probably don't know about, permittivity and permeability. There's gas constants. There's a bunch of just different constants that are used, that are found in nature, that are used. So Avogadro is one of them. And what it is it's a way that we can define something called a mole, M-O-L-E. And it's 6.022 times 10 to the 23rd particles. So a particle is just an object, right? So a particle could be a shoe, it could be a planet, it could be a star, it could be an atom, it could be an electron, whatever particle you're talking about, okay? And we define that number as a mole, and that'll be useful for us in chemistry, okay? So a lot of effort went in over a pretty long period of time to figure out what this number was or what this number could be. And, now it's known to many, many sig figs, okay? So we're going to define that as a mole, and the number itself, the 6 times 10 to the 23rd, that's actually called Avogadro's number. Sometimes it has a symbol, N sub A, and I'm going to write it this way, 6.022 times 10 to the 23rd per mole, per 1 mole, okay? I think that's a useful way to do it. Notice I'm abbreviating mole. I'm cutting off the E. That's just an abbreviation. You cut off the E and make it MOL, okay? So that's the number of particles in 1 mole. Just like you could say that you've got this thing called the dozen, and a dozen is 12 per dozen. Okay, that's the same kind of idea. It's just sort of a counting unit. Okay. And the thing about Avogadro's number is that it is connected to mass, is connected to how much things weigh. Okay. So what I want to do is I want to show you an example here. From Alex. So it's using the Avogadro's number. So they tell you that you got a brick. And this brick has a mass of 4 kilograms, 4.0 kilograms. Okay. So that's one piece of information. And then they tell you that the Earth has a mass is 6.0 times 10 to the 27. And they put it in grams. And this is just an issue with Alex. They really want to reinforce this idea of prefixes, using prefixes. So you're going to see problems where they give you kilograms for one number and grams for another, or micrograms for another, and you have to kind of convert back and forth. Okay, very common thing. So these are two masses. Now, generally, the mass of the Earth would be in kilograms. So it's a little bit of a stretch to put that one in grams, but that's fine. So now what they do is they ask you the following question. What is the mass of 1 mole of bricks? Okay, that's your first question. And then the second question is, how many moles of bricks equal the mass of the Earth? Okay, so it's actually kind of an interesting question because it sort of gets to this idea of transforming matter. So for example, people have talked about building something called a Dyson Sphere, which is the claim is that, advanced societies might be able to do something like that. So essentially what you do is you deconstruct a planet, you just tear up a planet and convert it into a shell that surrounds, the solar system. And then on the inside surface, you collect all the radiation that's coming from the star. So you imagine the star at the center, and then you've got this like little shell around it made out of metal, and it's absorbing all the radiation. And then you have all that energy that you can do pretty amazing things that we're not able to do right now. So that's called the Dyson Sphere. So the question then is, like, if you deconstructed an Earth, how many bricks could you make out of it? It's kind of cool. All right. So it's very simple, because the mole, when they say a mole, all you got to do is you got to say, wait a minute, 1 mole is equal to 6.022 times 10 to the 23rd particles. And here we're talking about bricks, right? So that's how many bricks are in a mole of bricks. Okay. So then what do? Then you say, okay, well, if 1 brick has a mass of 4 kilograms, how much mass would all of these bricks, 6 times 10 to the 23rd bricks weigh, right? You just multiply the numbers, right? Like if I had 1 brick is 4 kilograms, how much would 2 bricks weigh? It'd be twice as much, 2 times 4. If I had 10 bricks, it'd be 10 times as much, 10 times 4, and it'd be 40 kilograms, right? So if you have 1 mole, that's the number you have right there. So it's just going to be 4 kilograms times 6.022 times 10 to the 23rd bricks, right? So really it's 4 kilograms per 1 brick, if you want to use dimensional analysis, right? That's how much 1 brick weighs. So 4 kilograms per brick, I'm sorry, that's a 23, times this big number is going to give you the number of kilograms that a mole of bricks weigh. So just remember, a mole is 6 times 10 to the 23rd, okay? So 4.0 times 6.022 times 10 to the 23rd, and you're going to get this big number, 2.4088 times 10 to the 24. And then your units are going to be in kilograms. Okay. Now, if the Earth's mass had been 6 times 10 to the 27 kilograms, we would have a very simple problem here. But just keep in mind, they have this in different units, right? So you don't want to compare pounds to ounces or pounds to kilograms. You want to compare pounds to pounds or kilograms to kilograms. So since this one's in kilogram, we have a choice. We could either convert this one to kilograms, the Earth, or we could convert the bricks into grams. So one or the other, okay? I'm going to do the Earth. I'll convert the Earth into kilograms because most of the time the mass of the Earth is reported in kilograms, not in grams. It's sort of an unusual unit to have for it. So let's get back to the Earth. 6.0 times 10 to the 27 grams. That's how much the Earth weighs. That's how much mass it has. Now let's do a kilogram. Kilo is 1,000. The abbreviation for kilo is a K. 1,000, 1000. Sometimes written in exponential notation like that, right? So kilo is a K, it's 1,000 or 10 to the 3, either one. So the way you can do this is you say, look, what if I have a kilogram? So a kilogram is just kilos of grams. So that would be thousands of grams or 10 to the 3rd gram. That's really what a kilogram is. It's 1,000 grams, okay? So then what you do is you can say, look, I'm going to write it as a sort of little identity. 1 kilogram is equal to 1,000 grams. And that's a true statement, right? Like a kilo is 1,000 and a gram is a gram. So a kilogram is 1,000 grams. And that's your conversion factor right there. You can convert with this. Okay. So what you do is you take your 6.0 times 10 to the 27 grams and multiply it by, we want to go to kilograms. So I'm going to put this one on the top. So I'm going to put 1 kilogram over 1,000 grams. And what that's going to do is it's going to knock down that number by 3 because you're dividing it by 1,000. So that's like dividing by 10, by 10, by 10, 1,000. So you get 6.0 times 10 to the 24. And now it's in kilograms. Okay, so let's just, before we actually answer this part 2, part B, whatever you want to call it, let's just compare those numbers. They're not that far off from each other, right? If you look at it, they're both 10 to the 24. So they both have the same sort of general size. It's just this 6.0 is a little bit bigger than the 2.4. Okay. So now you can just do a little comparison. The question is, how many moles of bricks equal the mass of the Earth? Well, 1 mole is this number here. So all you need to do is to say, like, look, you know, if I had 4 eggs, how much of a dozen do I have, right? How many of these 4 eggs would go into a dozen? Well, you know, 4 goes into 12 3 times. So you'd say you'd have 3 groups of 4 give you a dozen. So the same thing here. All you do is you say, look, I'm going to round this. 2 point, so let's do the other one. It's 6 times 10 to the 24 kilograms is the Earth, and 2.4088 times 10 to the 24 kilograms is the bricks. So that's going to tell you how many of these bricks are going to go into the Earth. Okay, so 6.0 divided by 2.4088, and you get something like 2.5. I'm going to round it to here. And it's actually essentially saying 2.5 moles of bricks, right? Because this is a mole. That's how many moles of bricks go into the mass of the Earth. So actually the answer then is, if you were able to convert the entire Earth, every atom of the Earth, into bricks, you know, you just had some factory that made bricks, and people have talked about doing stuff like that, like taking an entire asteroid, you know, in between Mars and Jupiter, and just converting it into materials that you would build. Assuming that a brick is 4 kilograms, now that's the assumption, right? You could have big bricks, you could have small bricks. We know what the mass of the Earth is. That would tell you that if you counted the bricks in terms of moles, there would be 2.5 moles of bricks is how many bricks you would get out of the entire Earth, which is a lot. That's a lot of bricks, right? So the Earth completely is a big stack of bricks. All right. So so try that one. That's the sort of introduction. Now that notice that one is nothing really to do with chemistry, right? It's the mass of the Earth. It's the mass of a brick. Where's the chemistry in that? The whole idea behind that problem is just to get you familiar with the idea of the relationship between the definition of the mole, which is Avogadro's number, 6 times 10 to the 23rd, and to connect that to this idea of mass, that things have mass. So if you have a mole of those things, 6 times 10 to the 23rd of those things, the mass, the total mass would just be 6 times 10 to the 23rd times the mass of one of those objects. So in this case, it happens to be bricks. And really, it's just sort of a thought experiment that if I took the Earth and converted it into bricks, how many moles of bricks would I have? Just to kind of give you an idea of these relationships. But the key point for us as chemists is this idea here, that 1 mole is this number, and that if you know how much one of the particles weighs, if you know its mass, you can multiply that by this number here, Avogadro's number,
How are you?
and that will give you an idea of how much mass you've got. Okay.
Yes. 7309 fifth up.
All righty. Okay, so let's take a look at another example. I think I can just close that one off. All right. Okay, so the next one is calculating and using the molar mass of elements. Okay, the molar mass of elements. So in this particular problem, what they do is they say, hey, you've got some number of moles of an element. So in this case, it's 0.0200 moles of gold. Okay, the symbol for gold is AU. You can look that up in the periodic table. Okay, and then they want you to calculate the mass of the gold. Now, they don't tell you what units it's going to be in. So if they don't tell you, assume it's grams. They actually do tell you, because what they do is where you enter the answer, they put a little G there for grams. So they are kind of telling you what the units are, but they don't explicitly say it in the question. Okay. So what we'll do, just so that you know, you're gonna look these up in the periodic table. So gold is element number 79. The symbol is an A with a lowercase u, and it's 196.97. So this is called the molar mass. Now, you may have heard of it as being called the atomic mass, and there is a context where it can be called the atomic mass. We kind of covered that back in section 3.2. But in the context of these problems, you want to call it the molar mass. And this is essentially the mass in grams. So specifically, it's in grams. Okay, that's why it's useful for us. Of 1 mole of this element or the substance. Right? So if we're talking about gold, what we would claim is, looking on the periodic table, is that 1 mole of gold has the following weight, 196.97. Okay. So that's its molar mass. And notice the way I wrote this. I wrote this to kind of set it up as a conversion factor. Because what you can do with, this is called an identity. That's what some people call this. One thing equals another. 12 inches equals a foot is an identity, or 2.5 centimeters equals 1 inch. That's an identity. You can write this in two ways. You can write it as 1 mole of gold over 196.97 grams of gold. Or you can also write it this way. 196.97 grams of gold is the same as a mole of gold, right? So each element in the periodic table is going to have its own molar mass. They all have different molar masses. Some are so close to each other. Potassium and argon are pretty close to each other. They're both around 40. But for the most part, they're all different, right? So each element has its own molar mass. So you look those up in the table, in the periodic table. So what that allows you to do is this allows you to do conversions. So let me show you the conversion here. We're going to do moles into mass. So here's how you go about this. If you're going from moles to mass, you multiply by the molar mass. Okay, so you just take the number of moles they gave you and you multiply it by the molar mass, and that'll give you the mass. If they give you the mass and you want to go to moles, you do the opposite. You divide by the molar mass, right? So like, for example, if I said you want to do like 36 inches equals a yard, 36 inches. You know, if you're trying to get to yards, you divide by 36. If you're trying to get back to inches, you multiply by 36, right? So you're just multiplying or dividing. Same thing here. If you want to go from moles to mass, you multiply by molar mass. If you want to go from mass to moles, you divide by molar mass, and that'll give you the answer. Okay, so let's take a look at it. What I'm going to do is I'm just going to erase this here to give us a little more room. Okay, so you take the number they gave you, 0.0200 moles. And then, okay, now you ask yourself, what are you trying to do? You're trying to go to mass, right? So if we're trying to go to mass, we're going to multiply by the molar mass. Multiplying by the molar mass is this one here. When you're multiplying by the molar mass, that means the grams is in the numerator in the top. So you're going to multiply it by 196.97. I'm going to take the symbol. We don't need to write the symbol every time. Okay. And so I just want to point out what happens is the units, moles divided by moles, right? Really what you have here is moles over moles. So they cancel. And then you have grams. So it's times grams. So your answer will be in grams. And what you'll see when you do this problem is they're going to give you a little G for the units. So you know it's in grams. Okay. So all you got to do is multiply those numbers. You just take 0.02 times 196.97, and you get 3.9394 grams. And then let's just take care of the significant figures. They usually will tell you what they want. Calculate it and round your answer to 3 significant digits. So they're going to tell you round it to 3. So the way you round it is you start here on the left. That's the most significant value. So that's 1. The next most significant is the tenths column, so that's 2. The third, that'd be number 3 right there. The number that comes after it is a 9, so you want to round it up to a 4. So round it up to 3.94, and that would be 3 significant digits. And there you go. Okay. So in other words, 0.02 moles of gold has a mass of 3.94 grams. That's the relationship there. Okay. Had they given you the mass, let's say they gave you 0.02 grams of gold, then what would you do? Then you would come back over here. To go from mass to moles, we're going to divide by the molar mass. If you're dividing by the molar mass, that's this one over here, right? You're dividing by this number here, okay? So these are conversion factors. We use these molar masses as conversion factors, and they're kind of useful that way. This is actually one of the most important types of calculations you'll do in the entire course. it is really the standard calculation that we use in chemistry for a variety of different types of problems. And that's for the following reason. In chemistry, we can weigh things. And so, how much material you have is based, you determine that by weighing it. So weight or mass is important. The other thing is that the mole is our counting unit. So just like if you were dealing in eggs, you were selling eggs, you're not going to sell eggs individually. You're going to sell them in dozens, 12, 24, 36. Those are units of 12. So we call that a dozen. Same thing in chemistry. We use units of moles, 1 mole, 2 moles, 3 moles, okay? So mass is important because that's how we experimentally weigh it. Moles is important because that's our counting unit, but we need a way to go between those two units, and that's our conversion factor, which is the periodic table. The periodic table for all of these elements, right? Here's carbon. That's our conversion factor right there. This is what's going to let us go between mass and moles. And we can go either way, right? We can go between mass and moles with this 12.01. And so it's written as 12.01 grams of carbon per mole of carbon. So, if you start with moles and you multiply it by this, that's going to give you the grams. So that's your mass. So, right, multiply by molar mass to get the grams. On the other hand, if they give you the grams of carbon, well, then you divide. So you say 1 mole of carbon per 12.01 grams of carbon, and that's going to give you the moles of carbon. Okay, so it's just that conversion. I would write it on a 3.5. I would write it on an index card somewhere for you and just have it next to you, right? Just this little thing where, sometimes people do it this way. We like arrows in chemistry. We use them a lot, right? So mass, moles, okay? So if you're going from mass to moles, you divide by the molar mass. If you're going from moles to mass, you multiply by the molar mass, right? So that's that. Instead of doing it as two separate little equations, you can use it that way right there, okay? Now that's for an element. You can also do it for compounds. So you can do it for more complicated things. Okay, so here's an example. So this one is what we would call calculating and using the molar mass for heterodiatomic element compounds. So actually, let me dissect this a little bit. Calculating, they do like big words in the Alex software. Calculating and using molar mass of heterodiatomic compounds. That's kind of cool. Sounds complicated, right? So I'll talk about what that means in a moment. But in this problem, there's a chemist, and she weighs out some HBr. 105 grams of HBr, hydrogen bromide, okay? And you want to calculate the moles. Okay, so notice that in a way that's the same problem. We did, moles to grams and grams to mole for elements. Now we're just doing it for a compound. So the terminology here, heterodiatomic, what does that mean, right? So hetero means opposite or different, right? So hetero means, so like if you have a cat and a dog, they're hetero. The cat is different from a dog. If you have 2 dogs, they would be homo because they're the same. If you have 2 cats, they would be homo because they're the same, all right? So hetero just means opposite or different. And then di means 2. So hetero-di means 2 different. And then atomic means atoms. So heterodiatomic just means 2 different atoms. And that's exactly what you have here. HBr, two different atoms, right? You have a hydrogen atom and you have a bromine atom. The bromine atom is actually bigger than a hydrogen atom. So that's HBr. So that is a heterodiatomic compound. Now, if you had this, if you had two hydrogen atoms, this would be homodiatomic, right? Because it's the same two elements, hydrogen and hydrogen. So that would be diatomic and homodiatomic. If you had three atoms, like HCN, now you got three. So it's triatomic, right? So an atom is monatomic. A molecule with two atoms is diatomic. A molecule with three atoms is triatomic. So this would be a heterotriatomic compound, HCN would be. Okay, but that's not the issue here. All right, so let's take a look. What we said was, you know, when you have the mass of something and you want to calculate the moles, okay, you're going to divide by the molar mass. All right. The only issue is, what's the molar mass of HBr? Okay, well, here's how you calculate the molar mass. You start the same way you did before with gold. You go to the periodic table, but now you got two atoms. So you got to look up both of them. 35. Okay, so you got to look up both of them. And then you say, okay, well, how many hydrogen atoms are in here? It looks like there's one. So the molar mass would be one hydrogen atom, and each hydrogen is one. I'm going to write as grams per mole. And then you got one bromine, so 1 times 79.90. So when you get that, what do you get? That would be 80.91. Notice I'm writing it grams per mole. So that's how you get the molar mass of a compound. You just add up the molar mass of each atom that's in the compound, right? So like if you wanted to know what the mass of a car is, you would say, well, what's the mass of the wheels? What's the mass of the engine? What's the mass of the frame? What's the mass of the seats? You put it all together. You add it all together. Same thing for a compound. You just add up the molar mass of each atom that's in it. So that'll give you the molar mass for the compound. And then you can just go about the way we said before. You divide by the molar mass to get the number of moles. So 105, they didn't put a 0 there, they just put a dot. 105 grams of HBr. And then we're going to divide by molar mass. So remember, when you divide by molar mass, you can write it this way. You put the mole in the numerator, and you put the mass in the denominator. You know, you'll see me, sometimes I'll put the formula in when I do calculations, and sometimes I won't. It just depends on my mood. You don't have to put the chemical formula HBr every step. It can be useful sometimes to do that, but whatever. So grams cancels with grams, and you got your moles. So 105 divided by 80.91. And you get 1.2977 moles of HBr. And, you know, conceptually, if you think about it this way, when you calculate the molar mass, that's telling you how much 1 mole weighs. So if 1 mole weighs 81 grams, 80.91 is essentially 81, right? If you have 105, that's a little more than 81. So you got a little more than a mole, and that's what we ended up with. Now we go back and we ask, well, how many sig figs did they want us to have? They said 3. They said report it to 3, which is a common number of sig figs. So you start on the left. There's the first one. There's the second one. There's the third one. But the number coming after the 9 is 5 or greater, so you round it up. But when you round the 9 up, it becomes a 10, which means you got to round the 2 up and make it a 3. So it's actually 1.30. Which is kind of cool. Okay. So 1.30 moles of HBr should have a mass of 105 grams of HBr, okay? So notice this sort of common type of problem. We're converting between grams and moles and grams. The whole chapter, starting with section 3.4, is about converting between grams and moles. So you really want to get good at that because you'll use it again in chapter 4. You'll use it again in chapter 5. You'll use it again in chapter 10. And we don't really use it in 6 and 8 all that much. We could use it in 6, but we generally don't. We could use it in 8, but we generally don't. But in every topic of chemistry, the mass to mole conversion pops up, okay? How much does something weigh? Now, there was one other type of problem in there where they want you to do diatomic elements, and it's just, I just want to make a point here. So there are 7 diatomic elements in nature. Now we have to be careful when we say in nature, because usually what we mean is on the Earth. So depending on where you are in the universe, conditions can be very different. And when conditions are very different, what exists can be very different. So, you know, for the most part, the types of compounds we have on the Earth are the same as the types of compounds that you have in the atmosphere of Jupiter or Saturn, with the exception of organic compounds. Earth has a plethora of organic compounds, but, you know, HCN or CO2 or O2, you know, it's pretty much universal throughout the universe, at least in stars and solar systems. So 7 elements are what we would call diatomic on the Earth. And so I'm going to list them for you. The first one is hydrogen. And when we say it's diatomic, what we mean is it typically exists as 2 atoms. So it looks like this. That's diatomic, 2 atoms stuck together. When we get to chapter 8, we'll talk about what that means to say these 2 atoms are stuck together. We'll talk about that. Okay, so that's the first one. The second one is nitrogen, which is N2. And again, it's diatomic, which means that there are 2 atoms. Actually, let's make it a little bit bigger because it's bigger than a hydrogen atom. 2 atoms stuck together. What's interesting is there's 7 of them. It's not 14, it's not 0, it's not 1. There's 7 of these elements. Next one is oxygen. Oxygen is O2. Oxygen and nitrogen are pretty close to the same size. Fluorine is F2. And again, pretty much the same size. These 3 elements are about the same size. Actually, fluorine's a little smaller than oxygen, and oxygen's a little smaller than nitrogen, but they're all bigger than hydrogen. Next one is chlorine. Now, chlorine actually is a little bigger. It's bigger than fluorine. And then bromine. So we're getting close, right? I said there were 7. And then the last one is iodine. And you've probably heard of iodine. They use it as an antibiotic. Bromine you maybe never seen. Chlorine is a byproduct of bleach. So if you go to a swimming pool and it starts to smell like chlorine, you're not really smelling the salts that they put in there. You're smelling CO2 that's coming off as a gas. Under normal conditions, these are gases here. These first 5 are gases. The bromine is typically a liquid, and then iodine is a solid. So if you have iodine solution, you typically want to shake it up because there's solids in there, and you want that solid to kind of break up a little bit. Okay. So these are diatomics. So all the other elements are not diatomics, just these 7. There are a couple of elements that do some sort of strange things, like phosphorus forms 4 atoms. Sulfur sometimes forms 8 atoms. There's all kinds of different possibilities, but these are the seven important diatomics. And here's why it's important. You are often going to see problems in this chapter where they will say something like this: oxygen reacts with sodium, ... Okay? If you see a problem where they give you one of these 7 elements and they give you the name, but they don't give you the chemical formula, they don't say O, they don't say O2, they don't say O3, they just say oxygen reacts. So oxygen is all by itself. You assume it's a diatomic. Just assume it's a diatomic, unless they tell you otherwise. If they tell you otherwise, then that's fine. But typically they won't tell you, and that means it's a diatomic. So you would write it as O2. Now here's why that's important. Oxygen has a molar mass of 16 grams per mole. Oxygen O2 has a molar mass of twice as much because it has 2 atoms, right? So if you're doing calculation problems and you write it as oxygen plus sodium, you're going to probably get the wrong answer because you're going to have the wrong molar mass. You're going to use 16 when it's actually 32. So be careful. If it says oxygen reacts or bromine reacts or iodine is produced, you want to write these as diatomics. Okay. Let me show you where they are on kind of to look for patterns. Hydrogen is the first element. And then you come down to the second row and you've got nitrogen and then oxygen and then fluorine and then neon. So helium is up here, right? So there's your first row. Second row, you've got lithium and then you've got beryllium. And then over here, you got boron and carbon. So just so you know, it's these 3 right here, nitrogen, oxygen, and fluorine. These are diatomic. So is this one, right? And then what happens is the next one that's diatomic is here. The next one that's diatomic is here. And the next one that's diatomic is here. So actually 4 of them are in this one column. This is group 7A. This is group 8A. Okay, so this is sulfur, selenium, tellurium. This is phosphorus, arsenic, antimony. And then we don't need to worry about these ones, right? Okay, so it's this one right here, which is in group 1A, just hydrogen. And then you get to group 5A and group 6A, nitrogen, oxygen, fluorine. So look, you make this little kind of turn here, right? So it's those 6 right there. So if you have the periodic table next to you, you can remember it's just nitrogen all the way through iodine like that. Those are the diatomics plus hydrogen. And then, you know, if you think about it, our atmosphere is 78% nitrogen and 21% oxygen. It's really quite amazing what our atmosphere is like. It's 78% nitrogen, and nitrogen's N2. It's 21% oxygen, and the oxygen is O2. So there's only 1% everything else. All the gases that you hear about in the atmosphere other than nitrogen and oxygen, they all add up to 1%. Water, carbon dioxide, hydrogen, helium, neon, argon, chlorine, everything else is only 1% of the atmosphere. So that means that 99% of the atmosphere is comprised of diatomic elements, right? This one's diatomic and that one's diatomic. Okay. So that will help you when you do the problems where they want you to find the number of moles or they want you to find the mass based on that idea. Okay. All right. So that was section 3.4. What I want to do now is I want to talk about section 3.5, which is combustion analysis. Okay. So combustion analysis, combustion analysis is based on the following idea. There is a very important type of reaction that we perform in chemistry. It's important because it's essentially the type of chemistry that goes on in our bodies when we digest food. It also is important in terms of generating energy, which we'll talk about in chapter 5, through heat. So it's called combustion, and typically combustion is what's called a hydrocarbon reacting with oxygen. Oxygen, again, is diatomic to form carbon dioxide and water. But it also produces heat, which is a form of energy. We'll talk about that in chapter 5, okay? So I put an N here to indicate there's some number of carbon atoms. So N could be maybe just 1 carbon or 2 or 3 or 4 or 5 or 6, you know, whatever number. There's really, you know, we could go up to 1,000. And then the M is just the number of hydrogen atoms. And again, that could be, typically it's not 1. Usually it starts at least 2 or 3 or 4 or 5 or 6, so forth and so on. It can be a large number, okay? So that is called a hydrocarbon. Now, a hydrocarbon can also have oxygen, so it could be CnHm and then some number of O's. So I'll put a little P there, you know, where P is, you know, 1 or 2 or 3, so forth and so on. So that's also a hydrocarbon. These are all organic compounds. They react with oxygen to form carbon dioxide and water, and it's a very, very common type of reaction. So that's really the whole idea of this section, is to get us some introduction into this idea of combustion analysis, okay? So it starts with a very specific type of problem. And in this problem, it starts with percent mass, which is what we did back in section 3.2. And it was only 48 hours ago that I prepared that lecture for you guys. But, you know, that was section 3.2. So let me show you the first type of problem in this section. What they do, so this is elemental analysis of a binary compound. Binary means 2. Notice we have a lot of words for the same thing. Binary or di or hetero, you know, there's all kinds of different terms we use for the same thing. So in this problem, they give you 2 elements. And they don't give you the symbol, they just give you the name. So they tell you nitrogen, and then they tell you oxygen. And then they give you the mass percent of each. 26.0 and 74.1. Okay. And then they want you to find what's called the empirical formula. So the question is find, this is the task, the empirical formula of the compound. Now, back in 3.2, we did this kind of problem where we had the chemical formula like H2O, and then we did a calculation to figure out what the percentages of each element were in terms of grams, you know, mass percent. Here, you're just doing the reverse. You're taking the mass percent and then going back to find the chemical formula. But keep in mind, when you do this calculation, what that gives you is called the empirical formula. You get the empirical formula out of that, okay? So let me show you how you go about this. First of all, let's do the symbols, N and then O. And you might ask, well, wait a minute, didn't you say these are diatomics? You only need to deal with them as being diatomics in the context of nitrogen reacts with, or nitrogen is produced. Oxygen reacts with, oxygen is produced. In this type of problem, they're not telling you that. They're just saying, here's how much nitrogen is in this compound. Here's how much oxygen is in that compound. So you don't need to worry about them being diatomic, okay? It's only in the context that they say it's a reactant or a product, okay? This is a compound. So we know it's going to have a formula that could be this. This is possible. It's got a nitrogen and an oxygen. Maybe it's 2 nitrogens and 1 oxygen. That's possible. Maybe it's 1 nitrogen and 2 oxygens. That's possible. Maybe it's a nitrogen and 3 oxygens. That's possible. It turns out there's limits. We're not likely to have N7032. So we'll see as we go along the course what the limits are. But we don't need to know what the formula is at the beginning here because we're going to figure it out. So I'm just pointing out that the formula should look something like that. Some number of nitrogens, some number of oxygens, maybe 1 and 1, maybe 2 and 1, maybe 1 and 2. Who knows? Okay. So let's take a look at how you go about it. I'm going to write down their molar masses from the periodic table. Remember, that's grams per mole, right? 14.01 and 16.00, right? So I remember all these, molar masses just because I've done these problems for 20 years. You know, if you don't know them, you just got to look them up. It takes a little more time to look them up, but you can find them and you'll have them. Okay, so those are the molar masses. So here's how you go about it. If you look at those two numbers, they add up to 100%. They add up to 100, right? All that's saying is the compound only has 2 elements. So some of the mass is nitrogen, some of the mass is oxygen. So it's got to add up to 100% if those are the only 2 elements in there. So here's what we do, just to make our calculation simple. Start with nitrogen. Just assume that the percentage is proportional to the mass, right? The higher the percentage, the more of that element you have, the more mass it would have. The lower the percentage, the less of that element you have, the less the mass would be. So just assume it's proportional and just write it as 26.0 grams of nitrogen. Okay. Then convert to moles. So step 1, convert to moles. See how that converting to moles and grams is going to come up over and over? I'm telling you, it does. So we're going to convert it to moles. Well, how do we convert it to moles? We use the molar mass. So we say you got 26.0 grams. We said to get to moles, you divide by the molar mass. Okay, so that's what I'm doing. I'm dividing by the molar mass. So 26 divided by 14.01, and you get 1.856. Okay. Now I'm going to do the same thing for oxygen. For oxygen, we've got 74.1%. So I'm just going to say that's 74.1 grams of oxygen. Okay, that's how much oxygen you have. I don't need to write O again. Step 1, convert to moles. All right, so 74.1 grams of oxygen. To get to to get the moles, you divide by the molar mass. Right, so I'm dividing by 16, which is the molar mass. So 74.1 over 16, and you get 4.631 moles of oxygen. Okay. Yeah, I guess that seems about right. 74 divided by 16. Okay. So here's our 2 numbers. I'm running out of room here. So what I'm going to do is I'm going to be a little careful here. Really need to prepare a little better. Okay, so I'm just going to write these numbers down. 1.856 moles of nitrogen and 4.631 moles of oxygen. So that way we've got another slide. Okay, so 1.856 moles of nitrogen and 4.631 moles of oxygen. Okay, now here's the idea. When you get to moles, that is essentially how many of these atoms you have. So 1.856 moles of nitrogen is 1.856 times Avogadro's number, how many atoms you have. So it's really a measure of how many you have. Now what we want to do is we want to find the ratio. Now, how do you find a ratio? Let me show you an example. Suppose we said, let's use whole horses and ponies. Let's say that we have 16 horses and 4 ponies. Okay, we could write that as a ratio. We could say there's 16 horses for every 4 ponies. So that's a ratio of 4 to 1, right? It's really 4 to 1, right? 16 to 4 is the same as 4 to 1. So what that means is you've got 4 horses for every 1 pony, right? And we could write that as a formula. The formula of our little farm or ranch is there's 4 horses for every 1 pony. Now, suppose that I actually had a different ratio. So suppose I had 8 horses and I had 3 ponies. Well, if you do that, you get 2.66666666, right? Which is really 2 2/3, right? So now your ratio is 2 2/3 to 1. Now that's kind of an awkward way to report the ratio, 2 2/3 to 1, or 2.67 to 1. So typically what we do under those circumstances is we eliminate the little fraction here. We eliminate the denominator, the thirds. And how do you if you have remember how you do this is called a mixed fraction, and then you've got something called an improper fraction. All right. So the way you would deal with this is you'd say, 2 times 6 plus 2, right? Now we give you 8/3. Okay. So that's 8/3. Then you'd say, okay, well, what if I multiplied this by 3? Well, now the 3's would cancel and you'd have 8. And that's essentially what we're going to do with these types of problems. We're going to essentially get rid of any fraction that we have by multiplying by some small number, 2 or 3 or 4. So let's take a look at this one. The next step is to write a ratio, just like I did with the horses and ponies. You take, in general, you want to take the larger number and divide it by the smaller. So here's how you do it. You go 4.631 moles of oxygen, and you divide that by the smaller one, 1.856 moles of nitrogen. The reason you take the larger and divide by the smaller is you want to get a number that's bigger than 1. We don't want to have chemical formulas with 0.5 or 0.6. We want to have chemical formulas of 1, 2, 3, 4, 5 whole numbers. Okay. So 4.631 divided by 1.856, and you get, look what you get here. You get 2.495. That's your ratio. So that's to 1. So it's this to this is equal to this to this. So that's your moles of oxygen per moles of nitrogen. If we were allowed to write chemical formulas using decimal numbers, we would write it like this. We would write O 2.495 N, right? So remember, that means 1. When you don't write a number next to it, that means it's a 1. So we could write it that way, but that is just not allowed. We are not allowed. There's an agreement among chemists that we do not put in 2.495. We want to have whole numbers. So what we need is a ratio that's the same, a ratio that's the same as 4.631 to 1.856, but is whole numbers. It's got to be whole number, 1, 2, 3, 4, 5, 6. So how do we deal with that? The way you deal with it is you say, wait a minute, this is really close to 2.5. So it's really 2.5 moles of oxygen to 1 mole of nitrogen. Now that's still a decimal number. It's not a whole number. 2.5 is 2.5. So what do? You multiply by the smallest number you can think of that will convert this into a whole number. The smallest number you can multiply 2.5 by to get a whole number is 2. So now you get 2 times 2.5, which is 5. But if you're doing it to 1, you got to do it to the other, right? 16 to 4, you can't just multiply this by 3. That changes the ratio. But if you do this, multiply them both by 3, that ratio there is the same as that ratio there. So you can multiply them both by the same number. So same thing here. You got to multiply the 1 by 2. And so now you get 2 moles of nitrogen. So now what do we have? We have nice small numbers that are whole numbers. And that ratio right there is equal to that ratio right there. You can just do it by checking it. This divided by that is the same as this divided by that. So how do we write it as a formula? Well, we've got 5 oxygens, so it's O5. We've got 2 nitrogens, so it's N2. Now, typically when we write chemical formulas, oxygen comes after the nitrogen. So usually it's written as N2O5. But does it tell you to do it? It doesn't tell you which order you have to do it in. So it should be okay to put O5N2. But typically you put oxygen last. Okay. Let's try another one. So for this one, they have carbon, which is 42.9, and they have oxygen, which is 57.2. Again, they add up to 100. We want to find the empirical formula. All right. They call it compound X, right? So we know it's going to be like CO or CO2 or C2O or maybe C2O5 or C5O2. It's going to be some whole numbers. That's what we got to end up with. That's called the empirical formula. So carbon is C, oxygen is O, 12.01 is the molar mass, and 16.00 is the molar mass, grams per mole. Okay, so step 1, assume that they're, grams. So 42.9 grams of carbon, okay? Divide by the molar mass. So 1 mole of carbon is 12.01 grams of carbon. See, on this one, I wrote the symbols, but you don't have to. So 42.9 over 12.01. Step 1, get it into moles, 3.572. Do the same thing for the oxygen. So you've got 57.2 grams of oxygen. 1 mole of oxygen is 16 grams. So 57.2. And you get 3.575. Okay, next step. So this is really step 1 here. You're doing it for each one. If you had 3 elements, you would just do it for all 3. Find the moles of all 3. So that's step 1, convert to moles. Okay. Step 2, divide by smaller moles, smaller number of moles. Right, this is going to give you a ratio. Okay, so I'm going to, actually, look at them. They're almost identical. They're really the same. Okay, so technically this one's smaller, right? That's a little bit smaller. So we'll divide that. So I'm going to write moles of oxygen divided by moles of carbon. The larger one divided by the smaller one. So 3.575, 3.572. So when you do that, you get almost 1 exactly. So here's what you want to do. If the digit after the decimal point, that first digit, if it's a 0, just round it. Just round it to 1. The ratio is 1. If that digit is like 4.9 or 4.7 or 5.2, round it to 0.5. If it's around 0.3, round it to 0.33, a third, and so forth and so on. But if it's a 0 there, you know you've got a whole number. So just round it there. So that means really it's 1-to-1. So what you do is you say, okay, it's a 1-to-1 ratio. This divided by that is really 1-to-1. So that means it's just CO. That's a 1, and that's a 1. They're both 1. So your answer then would just be CO. Okay. Now, if you had gotten, 1.49, you would round that to 1.5 and then multiply them both by 2 to get them up to, whole numbers. And that's essentially how you go about that one. Okay. Okay, we got that type. Oh, shoot. Sorry, guys. I just messed up. Log back in again. Okay, there's really just, there's a couple of like little variations of this, but there's really just one more type of problem in this section. There we go. And that type of problem is what's called the molecular formula. Okay, so I'm going to show you this one. So this one puts it all together. So in a sense, this is the most complicated one, but it's not really that much more complicated. So here's what they do. So this is finding the molecular formula. That's our goal. And what they're going to do is they're going to say there's this compound. They're going to call it compound X. Chemists love X for unknown. It has a molar mass of 180.16 grams per mole. Now, I was pretty sure I knew what this compound is, but we'll have to check. Now, notice this one, they give you 3 elements. And it really doesn't matter how many elements you have. You can just go through it and do it the same way. Okay, and then they give you the mass percentages. Okay, there you go. All right, so you got 3 elements in this case, and again, they give you the mass percent. Now, notice in this one, you want to find the molecular formula. So let me talk just real briefly. I'll do that down here. The difference between empirical formula and molecular formula. This is just the ratio of the elements in the compound. Notice it's a ratio. Now, the significance of the term ratio is this. This is a ratio 1-to-1, right? But here's another ratio that is exactly the same. 2-to-2 has the same result as 1-to-1, right? 3-to-3, 4-to-4. So the problem here is that you can say, okay, it's a ratio of elements. The empirical formula is a ratio. But which ratio is it? Like, is it 1-to-1, or is it 2-to-2, or is it 3-to-3, or is it 4-to-4, or is it 5-to-5? The empirical formula is the smallest possible whole number ratio of elements in the compound. So the point here is it's the smallest possible whole number ratio. So it's not just any ratio, it's the smallest possible. So for example, if I had C5O5, that's a ratio 5-to-5. But it's not the smallest possible ratio. What we could do is we could divide each of these numbers by 5. And that would make it a different ratio. 1 to 1, right? Remember, if it's a 1, you don't write as number. You don't write 1 there explicitly, okay? So when it's the empirical formula, this ratio has to be as small as you can get it. So for example, if I had C6H4, what you would do is you would say, is there any number I can divide these two by to make them smaller but still be whole numbers? And for this one, if you divided this by a 2, you'd get a 3. And if you divided this by a 2, you'd get a 2. So it's still, this is the same ratio. 6 to 4 is the same as 3 to 2. But you want it to be the smallest possible whole. Now, there's nothing we can divide that by. 3 and 2, there's nothing we can divide them by to make them smaller, but still be whole numbers, right? So this would be the empirical formula right there. So the empirical formula is the smallest possible ratio of whole numbers. But in this particular problem, so that's why when you do those problems, you're not going to see C202. You're not going to get C202 or C306. It's always going to be, 1 to 1 or 1 to 2 or 2 to 1 or 2 to 3. 2 to 5 works because there's nothing you can divide 2 and 5 by that makes them smaller. Okay. This is molecular formula. What's the molecular formula? We know what the empirical formula is. The molecular formula is the actual number of atoms in the compound. So the molecular formula is more powerful. It's more useful, at least in some cases. It's the actual number of atoms. Of each element in the compound. So for example, there might be a compound N2O4, and the molecular formula, there is actually a compound called N2O4, and that would be the molecular formula. That it has 2 nitrogens and it has 4 oxygens. That's the actual structure. It looks like this: 2 nitrogens in the center, and then 2 oxygens attached to each nitrogen. Right? So the molecular formula is the actual formula for the compound. It's the actual number of atoms in the compound. In the previous problem, the data they gave us allowed us to find the empirical formula, but we weren't given enough data to find the molecular formula. So this differs in the following way. See how they give you this number here? In the previous problem, they didn't do that. They didn't give us this. So if they give us this number here, we can find the molecular formula. If they don't give us this number, we can only find the empirical formula. So the molar mass allows the determination, allows us to find the molecular formula. If we don't have it, if it's not given, then we can find the empirical formula using the procedure we just did, but we can't find the molecular formula. So that means someone's got to get this number somehow. And there are experimental ways to do that, okay? So really in this section, there's 2 types of problems. One is find the empirical formula. In that case, you're not given the molar mass. 2, find the molecular formula. In that case, you are given the molar mass. They're going to give you the molar mass for that one. So let's take a look at this one. Let me just go to a new slide. 46.71 and 53.29. So 46.71 and 53.29. Notice hydrogen is always smaller because it doesn't weigh very much. It's very light, so the mass percent is going to be very small. Okay. So let's take a look. Those are the things we gave. And then there's one more piece of information, which is the molar mass. Is 180.16 grams per mole. Okay, I think this one's going to work out to be glucose. It's probably going to work out to be C6H12O6, but let's take a look. Here's how you go about it. You use this at the end. Okay. So you use the same procedure we just did. So let me be formal about it. So step 1, Percentages convert to grams. Step 2, convert grams to moles, right? So remember how we did that? We divide by the molar mass. Okay. Step 3, divide each mole by the smallest. Now we got 3, so we'll say smallest number of moles, the smallest value of moles. Okay. Step 4, if we have, 0.5, multiply by 2, multiply everything by 2. If you have 0.33 or 0.66, multiply by 3, right? Why does that work? Well, 0.33 is a third, so multiplying by 3 gives you a whole number. If it's 0.66, that's 2/3, so multiplying by 3 will give you a whole number. If you have something like 0.25 or 0.75, you multiply by 4, right? Because 0.25 is a fourth, so a fourth times 4 is 1. 0.75 is 3/4. 3/4 times 4 is 3, so that gives you a whole number, right? If you have a number like 0.2 or 0.4 or 0.6 or 0.8, well, the next number in the series is multiply by 5, right? Because this is really 1/5, 2/5, 3/5, 4/5, so you multiply by 5. And I'd be amazed if they make you go any beyond that. But if you were going to do by 6, it'd be like 0.166, 0.33, stuff like that. But in any case, so that's how you go. And then that's going to give you your formula. So let's do step 1. I'm going to do some of the work up here. Step 1, make this grams. 40 grams of carbon. 6.71 grams of hydrogen, right? You're just converting it into grams. Okay. The real trick in this is, how did they get those percentages? We didn't tell you how they got those percentages. That's a whole topic. It's a whole field of chemistry. How do you figure out what those percentages are? Nowadays, we build machines that will tell us, right? We build a device called a mass spectrometer, and the mass spectrometer will it will ionize, it'll put the stuff in a gas phase, it'll ionize it, it will accelerate it down a chamber using voltage and magnetism, and then it will use a detector to determine how much is in there and then compute out a percentage. So, we're ignoring that whole aspect of analytical chemistry in here of how do you get these percentages. But once you got the percentages, just assume they're grams. Step 2, divide by the molar mass to get moles. So I'm going to do it this way. 1 mole of carbon is 12.01 grams, right? I know that's very small, so I'm sorry, it's hard to see that. Dividing by 12. 12.01 is the molar mass from the periodic table. So 40 divided by 12.01, and you get 3.331 moles of carbon. I'll make that one a little bigger. So this is hydrogen. So again, 1 mole of hydrogen is 1.01 grams. That's the molar mass. So 6.71 over 1.01, and you get, to me, it looks like it's a 2-to-1 ratio. .644, yeah. If you look at those two numbers, 3.3 times 2 is 6.6, right? So it looks like it's a 2-to-1 ratio. And then we do the oxygen, multiply it by 1 mole of oxygen is 16 grams. So 53.29 divided by 16, and you get 3.33 again. Okay, so I just did step 2. We divided by the molar mass. That's the easy part, right? The trickier part is like to figure out what these ratios are. But, sometimes you can just eyeball it. If you just look at it, look, 3.33 times 2 is 6.66. That's pretty close, right? So it looks like it's a 1-to-2 ratio. And then the oxygen, 3.33, it's the same as carbon. So carbon and oxygen are 1-to-1. But let's go through it. What you do is you divide all three by the smallest. The smallest is either this one or this one. They're the same. So that's fine. So let's do carbon, hydrogen, and oxygen. So what I'm going to do is I'm going to take the number I have here, and I'm going to divide it by the smallest, which is 3.331. That gives you a 1, right? Because you're dividing it by itself. The second one, 6.644, divide that by the smallest, 3.331. Now, that's not exactly a whole number, but let's see how close it is. 6.644 divided by 3.331 is 1.99. Okay? So if you're at 1.99, that's not, 1.5, it's not 1.6, it's really close to 2. Okay, so we can round that to 2. And then the last one is 3.31. So 3.331 over 3.331. So that's 1. So right there, we've got the empirical formula. That's what we would have done in the previous 2 problems. Okay, so you got 1 carbon, 2 hydrogens, 1 oxygen. We don't have to multiply everything by 2. It's not 0.5. We don't have to multiply by 3. It's not 0.33 or 0.6. Those are all nice whole numbers. So we're done. We don't have to do, for this example, we don't have to do step 4. We don't need to do that. Okay. So that means it's just C, H2O, right? That'd be CH2O. That would be your empirical formula. They're all whole numbers. You cannot divide them by anything to make them smaller and still be whole numbers, right? If you divide it by 2, you get a half for carbon and oxygen. So that's a good empirical formula. The smallest whole number ratio of atoms. This is CH2O. So it's looking like a monosaccharide. It's looking like a sugar. A monosaccharide typically has either 5 or 6 carbons and some number of hydrogens. So it's we're gonna get a monosaccharide out of this. So it could be glucose. I guess it could be I think it's galactose is the same formula as glucose, but that gives us the empirical formula. So we got one more step. The last step is to find the molecular formula. And again, what I said was you got to have that number given. We can't just like pull it out of the air. You got to know what this is. It's got to be given right there. If you have that number, you can do the last step. So luckily they gave it to us. So let's do the last step. So what you do, come on. What you do, oop, I've created the maximum. I'm sorry. Do all what much. Okay, that's done. All right. Oh, a lot of technical issues today. So now what you do is you take your empirical formula and then you take your molar mass. Okay, now here's what you do. This is the molar mass of the actual compound. Okay. What's the molar mass of the empirical formula? Let's calculate that. There's 1 carbon, 2 hydrogens, and 1 oxygen. Now, if you do that calculation, it's what, 30.03 grams per mole. Okay, so if I had gotten 180, that would tell us that the empirical formula has the same weight as the actual compound, and that means it is the actual compound, right? Like if I'd gotten 180 here, that would be our answer. The molecular formula would be, CH2O. But you got 30. 30 is a fraction of 180, right? 180 is bigger than 30. So I'm going to give you a little analogy. Imagine it this way. Imagine that I told you the total weight of a short train. Let's say this train has 4 cars. Suppose I told you that this entire train weighs let's do 500. 500 tons. Okay, that's how much the whole thing weighs. And then I told you that one of the cars weighs 125 tons. We're going to assume all of the cars weigh the same, right? So they all weigh the same. So one of them weighs 125. We could then calculate, using those two numbers, how many cars there are, right? How many cars are in the train. What you would do is you'd say the total weight is 500 tons, and one car is 125 tons. So you would take your total and divide it by the weight of one of them. And then that would give you the number of cars, and it would come out to 4 cars, right? And let's just see if that works. If each one weighs 125, it'd be 125, 250. 125 would be 375. 125 would give you 500. So it works out. It's 4 cars, right? So what did I do here? I took the total weight and I divided by the weight of one of them, took that ratio, and that told me how many of the cars there were, right? Same thing here. The empirical formula is essentially a fraction of the total. It's, half the total or a third of the total or a quarter of the total. The molecular formula is units of the empirical formula, and it has to be a whole number. So what you do is you take the molar mass of the compound, so that's got to be given, 180.16 grams per mole. So that one's given. And then you divide it by the molar mass of the empirical formula. That you got to calculate, right? I already did it. That's up here, right? So you take your empirical formula, you just add up the atomic mass, you just add up the molar masses of each atom, and of each element, and then that will give you the empirical formula. So that's 30.03. Okay. Now look what happens. When you do that, you get 6. It comes out to 6, right? It's almost exact. It's 6.0 something, right? But it's essentially 6. So what that means is you've got 6 of these units in the actual formula, 6 of them. So it's really, you can think of it as CH2O, CH2O, just like the train, CH2O, 6 of them. But we don't write it that way. That's not a chemical formula. That's a little picture. So how do we write it as a chemical formula? If I have twice as many carbons, I double the number of carbons. If I have 6 times as many carbons, I multiply that number by 6. So what you do is you take your CH2O and you multiply the subscripts by 6. So remember, this is a 1 here. We're not really writing it as a 1, but it's implied that that's a 1. So 1 times 6 is a 6. Now that is a 2. It's explicitly shown. 2 times 6 is 12. And again, there's a 1 there. So 1 times 6 is 6. And that would be your molecular formula. So that's it right there. Okay. So a lot of steps in there, right? So just to kind of review it, the way you go about, I'm not going to erase that yet because you might still be looking at it. The way you go about it is you're given the percentages of each element. So you assume those percentages are grams. You divide each element grams by molar mass to get the number of moles. You now have the moles of everything. each element. Could be 6 elements. So you have the number of moles. You divide each mole by the smallest of them, okay? Once you do that, you're going to get these numbers that could all be whole numbers. You might get 2, 3, 1. You might get 2, 3, a half. Well, actually, you might get 2, 1, a half. If you get a half or 1 and a half, you just multiply everything by 2. If you get a third or 2/3, you multiply everything by 3. So now you're going to have a bunch of whole numbers, and that's your empirical formula, right? This was a 1, this was a 2, this was a 1. So our empirical formula was CH2O. That gives you the empirical formula. You got it. Then they're going to give you the molecular formula's molar mass, which is right here. So then you say, okay, I've got the empirical formula. How much does that weigh? There it is. I calculated it. You take the molar mass of the compound, divide it by the molar mass of the empirical formula, and that will give you a whole number. It's not going to give you 1.5 or something like that. It's going to give you a whole number for that step. So in this case, it turned out to be 6. So you take your empirical formula and you multiply it by that ratio. So that ratio here was 6. And then you just change, remember, you change the subscripts. So if the subscript was 1, 2, 1, you change the subscripts to 6, 12, 6. So suppose that they had told you in this problem that the molar mass wasn't 180.16, but it was 90.08. Well, then you would take 90 divided by 30, and that would give you 3. And then you would take 1 times 3, 2 times 3, 1 times 3. So you'd get 3, 6, 3. And that would be your molecular formula. Okay? So I did that very quickly, just because we were running out of time. But you can watch it again, once it's uploaded. You can watch it a couple of times if you want to. I also did a couple of these last semester, so if you want to see even more videos on it, you can look back at last semester for the section 3.5. And that pretty much completes that section. So again, I'm sorry about tomorrow, but tomorrow I'm going to reschedule the lecture for Friday morning, 9 to 10:30. And so on Friday, I will do calculations with balanced chemical equations, 3.6, limiting reactants, 3.7, and that will wrap up chapter 3. So, so tough course, right? It's tough. The pace here is intense, 6 weeks. But I have actually seen schools where they try to do it in 4 weeks. So that's really intense, but we're doing it in 6, okay? So call or text me or email me if you have any questions today. And again, I will see you on Friday morning, okay? Take care, everybody. Have a great day, okay?
Thank you.
Thank you,
Thank you,
Professor.
Professor.
Thank you.
Thank you.
Thank you so much. Bye-bye.
Bye. Thank you.